The problem we're going to look at today is problem 9.24 from Fundamentals of Heat and Mass Transfer by Bergman and Levine. The question is given as follows. It says, consider the conveyor system described in problem 7.24, but under conditions for which the conveyor is not moving and the air is quiescent. Radiation effects and interactions between boundary layers of adjoining surfaces may be neglected. The first problem that we're asked to solve is A, which is for the prescribed plate dimensions and initial temperature, as well as the prescribed air temperature, what is the initial rate of heat transfer from one of the plates? And then in problem B, we're asked to solve how long does it take for a plate to cool from 300 C to 100 C? Comment on the assumption of negligible radiation. So our knowns, which are given to us, is we know that the plates are AISI 1010 with these material properties taken at the film temperature. We know that the plates are 6 millimeters thick and have a length on each side of 1 meter. Our free stream velocity in this case is going to be 0 since it's free convection. Our ambient temperature is going to be 20 degrees C. Our initial temperature of the plates are going to be 300 degrees C, and our calculated film temperature is going to be about 160 degrees Celsius. So what we need to find in A, we need to find the initial heat transfer rate, or H. And for B, we need to find the time that it takes the plate to cool in T seconds. Our schematic is going to look like this. So we have these plates, they're suspended in air, and they're not going to be moving, and there's going to be no airflow in the room. So it's just going to be cooling by pure natural convection. To do that, we're going to assume that it's going to be constant properties. So the properties of the air and the plate are not going to change over time as the temperature changes. We're going to neglect radiation for the first problem. We're going to neglect the conveyor movement. So in this case, the conveyor is not moving, so there's no additional cooling from that. We're also going to neglect the adjacent plates. So we're going to take these as isolated flat vertical plates instead of two parallel plates. And we're also going to evaluate all the fluid properties for the air as well as the material at the film temperature, or TF. So for our first calculation, the first thing we're going to do is calculate our Grashof number. And we can do that by taking G, which is the gravity, or 9.81, times beta, which is the expansion coefficient. And in this case, since we're assuming air is an ideal gas, we can actually take beta to be equal to 1 over the temperature, or the film temperature. So in this case, we're going to do 1 over 433, and this has to be in units of Kelvin. Then we're going to take the difference in temperature, so the initial temperature of the plate, or TS, minus the ambient temperature, times our characteristic length cubed, which in this case is just going to be 1 meter, over the kinematic viscosity squared. And when we plug that all in, we get a Grashof value of about 8.48 times 10 to the 9. We can then also calculate our Prandtl number, which is going to be mu, the dynamic viscosity, times Cp, the specific heat, over Kf, which is the thermal conductivity of the fluid. When we plug in all those numbers, we'll get a Prandtl number of the air of about 0.6922. We can then use these two values to calculate our Rayleigh number, which is just going to be our Grashof number times our Prandtl number. And that's actually, we have a small typo here, but we're going to use this value of 8.48 times 10 to the 9th. Multiply that by our Prandtl number, and that's going to give us a value of about 5.87 times 10 to the 9th. So the critical Rayleigh number, which is kind of analogous to the Reynolds number for a forced convection case, it's going to tell us when our boundary layer is going to go from a laminar to turbulent flow. And in this case, the critical value is about 10 to the 9. So since we're at 5.87, 10 to the 9, we're going to assume that our heat transfer is turbulent. So there's actually a few different ways, or a few different empirical calculations that we can use to calculate this number. But in this case, we're going to use this pretty general form, which is the Churchill-Chew correlation. And it takes the form as this. So our Nusselt number over the length, or our average Nusselt number, is equal to our average heat transfer coefficient times our length divided by K, the thermal conductivity. And that's all going to be equivalent to this kind of nasty looking equation, which is going to be 0.825 plus 3.87 times our calculated Rayleigh number to the 1/6 over 1 plus 0.492 over our calculated Prandtl number to the 9/16, all of that to the 8/27. And then we're going to square that entire equation. And when we plug in all of our values that we calculated up here, we're actually going to get a Nusselt number of 212.52. And when we solve for H by multiplying by our thermal conductivity and then dividing by our length, we'll actually get an average heat transfer coefficient of about 7.2957 watts per meter squared Kelvin. So we can then take our calculated average heat transfer coefficient, and we can actually use this equation to calculate the cooling time. So this is going to be T is equal to M, which is the mass of the plate, times Cp, which is the specific heat, over H, our calculated heat transfer coefficient, times A, which is the area that the heat transfer coefficient is acting over. And we're going to multiply that by the natural log of our initial temperature minus our ambient temperature over the temperature we're asked to find. In this case, it's going to be 100 degrees C because we're asked to find when the plate cools to 100 degrees C, again, minus the ambient temperature. First thing we'll do is just quickly calculate our mass of the plates, and that's just simply rho V. So rho times the volume of the plate. So 7,832 times 1 meter times 6 millimeters. And that's going to give us that each plate weighs about 46.992 kilograms. And we can then take that mass value, we can plug it into our equation here, and as well as our temperatures. And the one thing to note that our area on the bottom here is actually going to be 2 square meters since we're cooling on both sides of the plate. And when we plug in those values, we can see that the plates with just natural convection are going to take about 1,747 seconds to cool, which is roughly about a half hour. So the next thing we're asked to do is to comment on our assumption of radiation and the fact that we neglected it for our calculation. So the first thing we can do is we can find our heat transfer rate that we're getting from our convection by simply taking HA delta T. So we'll take our average heat transfer coefficient of 7.2957. We'll multiply that by the area on each side of the plate, which is going to be 2 square meters, times our temperature difference, which is going to be 280. And we'll find that our average heat transfer from convection is going to be 4,085 watts roughly. And again, this is our heat transfer coefficient going from our initial temperature all the way down to ambient. So it's going to be 280 here. And we can also calculate our radiation value by using this equation. So we'll take eta, the emissivity, times the Stefan-Boltzmann constant, times our area again. And then we're going to take the change in temperature to the fourth. And the one important thing to note here is what we select for our emissivity of the plates. And in this case, since the plates just came out of a heat transfer process, they're likely going to be heavily oxidized and have a thick scale on it. And if we look up the value for oxidized steel, it's around 0.8. So we're going to use 0.8 in this equation. Again, we'll multiply that by our Stefan-Boltzmann constant, multiply it by our area of the 2 square meters for each side of the plate. And then we'll take our initial temperature to the fourth minus our ambient temperature to the fourth. And what we can see is that we're actually going to get a heat transfer rate from radiation of about 9,111 watts. And if we compare that to our convective heat transfer, we can see that our heat transfer to radiation is almost 2 times our natural convection. So if we wanted to actually get an accurate value for how fast this plate is going to cool, we really should add the radiation value into our calculation. If we neglect it, this plate is going to appear to take a lot longer to cool than it really will in real life when we neglected this radiation.